the arc length in the 2 space. Here we consider the arc length on a smooth curve. Just a note in terms of the arc length and where the notation came from. Now you check this guy out right here. Now this guy is put together, I tell you. You know, I always thought that that the Jackson 5 created and started the Afro, but now we know that it did not come from the Jackson 5. It came from this guy right here, the original Doobie Brothers, the Brothers Johnson. This guy has a cool set of hair on top of his head. Just wanted to note that. I thought that would be interesting. As we continue on, the arc length. In this section, we will discuss how to calculate an arc length. It is important that the area or the space that we calculate the so-called arc length is smooth. And the definition for smooth or smooth curve is that all the points along the curve or closed interval from A to B, all the points on the function are said to be not only continuous, but the derivatives exist at each point. And so we say that the function is continuously differentiable on that particular closed interval. Thus, we have the idea of a smooth curve. We say that the curve is rectifiable in that the curve has a finite arc length. That is important because there are times that we can discuss in an infinite dimensional vector space an infinite set of curvatures that would denote some type of arc length out in space. So we use the distance formula, and if I had time, I would go through this with you, but I just left it with the author and his explanation. I do have an explanation for it where I try to simplify all of that, but I will spend more of my time working some problems in this section. We denote S here. We take the summation of partitions of these rectangular slices that we get from the distance formula. See how the distance formula matches up in this summation. The difference of the x values, delta x sub I, the difference of the y values, delta y sub I. What we do there in that proof is that we divide out delta x squared, and because the delta x, one of those guys, would actually give us our differential, our dx, by which we want to calculate the integral. The summation gives us the integral. We take this delta x squared and we factor it out. And when we do, we bring it out of the radical that has left a delta x on the outside. And then in the radical, we have the 1 plus the ratio of delta x over delta y divided by delta x to be squared. Well, that this difference quotient will, based on the limiting process, give us a derivative, and that's simply just y prime. So the summation of the radical of 1 plus y prime to be squared, and this is dx, and the summation turns into the integral over the limit. So here, this limit is read as this is the norm, and it's the measure of the partition and the standard partition that we call delta is equal to b minus a over n is the partition that you want, and you want to take as n goes to infinity, we say that the partition shrinks. And so we have these slices of rectangles here, and you want to to minimize those rectangles. Make them as thin as possible, thus giving you not the area under the curve, but this square root gives us a point on the curve, and then the summation, you add up those points and we get the arc length. So the definition of the arc length given here, the arc length S, we say that the function f is a smooth curve. That is that the curve is continuously differentiable on the closed interval from A to B. Another phrase for that, in some of the older books, they talk about rectifiable curve. So we calculate the arc length as the integral from A to B of the square root of 1 plus f prime of x to b squared dx. Now we just go right to the problems. So we're going to use that formula to calculate the arc length. Let's take this problem here. Well, you know, in the formula it calls for several things, and particularly we want to take the derivative of f, and then we're going to square it, add 1, take the square root of that, and then integrate all of that. We're integrating here A to B. We're integrating from 0 to 1. Oops. So y prime is 2/3 times 3 over 2 times x squared plus 1 to the 3/2 minus 1, or minus 2 over 2. We have left 1/2 times the derivative of the inside, which is 2x. We simplify that, and the y prime gives us 2x times x squared plus 1 to the 1/2 power. So the arc length is the integral from 0 to 1 of the square root of 1 plus this derivative squared, so 1 plus 2x times the square root of x squared plus 1 to b squared dx. So the arc length is the integral from 0 to 1 of the square root of, let's see what we have. This is 1 plus 4x squared times x squared plus 1 dx. So the arc length is the integral from 0 to 1 of the square root of 1 plus 4x to the 4th plus 4x squared dx. We continue to simplify. This is the square root of 4x to the 4th plus 4x squared plus 1 dx. We can factor that, so this is the integral of the square root of 2x squared plus 1 all to be squared. So here the arc length gives us the integral from 0 to 1 of 2x squared plus 1 dx. We integrate now, so we get 2x to the 3rd over 3 plus x. You evaluate all this from 0 to 1. So we get 2 over 3 plus 1. That gives us 5/3 for the arc length. Let's take the next one. I think I can make use of our space. So for the arc length, we need the derivative. So this is 2/3 times 3 over 2, so that's going to cancel out, times x to the 3/2 minus 2 over 2, or x to the 1/2 power. And so the arc length is the integral from 0 to 1 of the square root of 1 plus x to the 1/2, and that's to be squared, dx. So the arc length is the integral from 0 to 1 of the square root of 1 plus x dx. If you let u equal to 1 plus x, this implies that du is dx. So the arc length is the integral from 0 to 1 of u to the 1/2 du. So now we integrate. So this is u to the 1/2 plus 1 is 3/2 all over 3/2. And the x plus 1 is being evaluated from 0 to 1, not u. So I'll go back and correct that. So this is 2 over 3, and the u was the 1 plus x to the 3/2 power. That's evaluated from 0 to 1. And so we have plug in x to equal to 2. So we have 2/3. And so this is 2 to the 3/2 power, which is the same thing as 2 times the square root of 2, minus evaluate 1 plus x to the 3/2 at x equal to 0. And that just leaves us with a minus 1 times the 2/3, but we have that in parentheses. So we'll just say minus 1. The computer may want you to calculate the decimal of that, so just do it. That's elementary, so I'll leave that to you. Here's another one. So we need the derivative. So y prime is 5x to the 4th all over 10 plus, this is 1 over x times x to the negative 3. So this is x to the negative 3. And maybe I need to rewrite that. Yeah, let's do that. So let's write y as x to the 5th over 10 plus 1 over 6 times x to the negative 3. So now this implies that y prime is the 5x to the 4th all over 10 minus 3x, and negative 3 minus 1 is to the negative 4, and it's over 6. We simplify that, that's x to the 4th over 2 minus 1 over 2x to the 4th. Okay. We can factor out a 1/2. So we have there times parentheses x to the 4th minus 1 over x to the 4th. So now we have to square that guy. So this is y prime to be squared. So this is 1/4 times x to the 4th minus 1 over x to the 4th to be squared. So this is 1/4, and this is x to the 8th minus 2 times x to the 4th divided by x to the 4th is just minus 2. And then this is plus 1 over x to the 4th to be squared. So this is plus 1 over x to the 8. Okay, and so now let's go ahead and add the 1, because you know the arc length formula has the square root of 1 plus y prime to be squared dx. So we got y prime to be squared. Let's just add a 1 to this expression so we'll know what goes under the radical. And so hopefully something would simplify. So 1 plus y prime to be squared is 1 plus, I'm just going to run that 1/4 through. So 1 plus 1 over 4 x to the 8 minus 1/2 plus 1 over 4 times x to the 8. So let's write that 1/4 x to the 8, the big term first. And this is plus 1/2 plus 1 over 4 times x to the 8. Now, it looks like a perfect square. It's weird, but it is. Let's maybe fract out a 1/4. It's going to work the way this guy worked here. So let's see. See if you see it. Take out a 1/4, so this is x to the 8th. It's going to be plus 2. So 2 times a 4th gives us a 1/2. And then this is plus 1 over x to the 8. So this guy is similar to this guy, but this was a negative there, no problem. So this 1 plus y prime to be squared is 1/4, and this is x to the 4th plus 1 over x to the 4th, all to be squared. So now we compute this arc length. This is the arc length. We're going from 2 to 5. And so this is the square root of this term, right? So it's the square root of 1/4 times x to the 4th plus 1 over x to the 4th to be squared dx. This is the integral from 2 to 5. And we can get rid of the radical. So this is 1/2 times x to the 4th plus 1 over x to the 4th dx. This is the integral from 2 to 5 of x to the 4th over 2 plus 1/2 times x to the negative 4. So I can integrate it directly. So we integrate, so this is x to the 4th plus 1 is x to the 5 all over 5 times 2 is 10. So let's see, we have plus, oops, good. So again, plus, we integrate that x to the negative 4. There's x to the negative 4 plus 1. That's x to the negative 3. X to the negative 3 all over 2 times a negative 3. Just say a negative 6. This is being evaluated from 2 to 5. So this is x to the 5th all over 10 minus 1 over 6 times x to the 3rd, evaluated from 2 to 5. I thought that was an interesting function because it seemed like we almost got the original function, but in terms of the signs, this is a plus sign there, and then over here it's a negative. Everything else was about the same. So we almost went in a circle. Boy, we've got some theological and some philosophical views on that. But anyway, so we plug in x to equal 5. So this is 5 to the 5th over 10 minus 1 over 6 times 5 to the 3rd. And then minus 2 to the 5th over 10 plus 1 over 6 times 2 to the 3rd. And on the calculator, let's see, where did I get that guy? On the calculator, you plug all that in and we get something around the neighborhood of 309.32. Okay. So that was number 9. Did I skip a problem? 3, number 5. It's number 9. Okay, number 11. Good. Yes. I'm doing what I'm supposed to do. So again, find the arc length. We need y prime. So this is the derivative of the natural log of something is 1 over that something times the derivative of that something. So this is 1 over sine x times the derivative of sine. We get cosine x. So here we get cosine x over sine x, which you know that that's no more than just cotangent x. I don't want to jump the gun. Okay. Good. And then the arc length is the integral from pi over 4 to 3 pi over 4. This is the square root of 1 plus cotangent squared x dx. Now that 1 plus cotangent x, what is that? Well, let's see if you forget. Just think about cosine square x plus sine square x is equal to 1. We want to build a cotangent, so we have to divide everything here by sine square. So we do that. We have cosine square x divided by sine square x plus sine square x divided by sine square x is equal to 1 over sine square x. So this is cotangent square x plus 1 is equal to cosecant square x. So that's what that is. So this is the integral from pi over 4 to 3 pi over 4. It's the square root of cosecant square x dx. So this is the integral from pi over 4 to 3 pi over 4 of the cosecant x dx. Now it's a known form there. So the arc length is the natural log of the absolute value of cosecant x minus cotangent x. That's being evaluated from pi over 4 to 3 pi over 4. So we plug that information in. We have the natural log of the absolute value of the cosecant. I'm going to write that as that's just 1 over sine. So this is 1 over sine of 3 pi over 4 minus the cotangent, which is 1 over tangent. You're dealing with the power of 4, so cotangent, or excuse me, tangent of power of 4 is equal to 1. And likewise with cotangent, just want to be mindful of where that angle shows up on the unit circle. So this is minus cotangent 3 pi over 4, then minus the natural log of the absolute value of 1 over sine of power over 4 minus cotangent of power over 4. So the arc length is the natural log of the absolute value. Now sine of power over 4 is 1 over the square root of 2, and 3 pi over 4 will put us in the second quadrant. So in the second quadrant, y is positive. So this is positive 1 divided by 1 over the square root of 2. That just comes out to be the square root of 2. Minus here for the cotangent of 3 pi over 4, the reference angle for that degree value would give us 1, but since it's cotangent, it's in the third quadrant, so that's the cosine divided by sine, so that's negative divided by positive, so we get negative 1. Minus the natural log of the absolute value. Here, sine of power of 4 is 1 over the square root of 2. 1 divided by 1 over the square root of 2 is just the square root of 2. And then minus cotangent of power of 4 is just 1. So this gives us the natural log of 1 plus the square root of 2 minus the natural log of the square root of 2 minus 1. So the arc length is the natural log of 1 plus the square root of 2 all over the square root of 2 minus 1. And on the calculator, when you calculate that, you get 1.763. Thank you. If you have any questions, just get in contact with me and I will help you out.